What is up, most distinguished patrons of this channel? It's been a while since I did a how-to video, so today we're going to be tackling how to weld rod ends, Heim joints, and that sort of stuff for steering and suspension components or whatever else you might be using these for. So let's get into it. So I have well over multiple hundred videos on how to weld and very few videos on how to weld stuff with some kind of liability, and that's going to be what this video is. Obviously, if you're building suspension components and steering systems for a car, be it on-road or off-road, there's liability there. And this is one of those things that I didn't want to get into right away because, well, for one, I need to have some content that'll teach you how to weld so you can weld these. And two, I need to build some confidence that you have an understanding of what's going on before you tackle something like this, because these are the types of components that you can weld that could end up failing and hurting yourself or other people. You get the idea. Now, I'm not head of safety here, and I don't really care what it is that you do with your welder in your shop. But the goal here is to get you to where you understand what's going on here and that you can competently take a job like this on and do it safely. So this is one of those things, number one disclaimer, if you can't make solid lap welds, fillet welds, etc. on 1/4 inch, 3/16, 1/8 inch, etc., you probably shouldn't be tackling this job. I hate to tell you, buddy, but that's just the truth. If you put down poor welds on this and it happens to be on a suspension link and you hit a bump off road or something that tears off and somebody gets hurt, well, it was avoidable had you just not done the job and paid someone competent. Now, with that said, I do believe that with some practice and a decent amount of skill, this really isn't that hard of a challenge. So don't get me wrong, this isn't impossible, but I have to put this out there so that you understand where I'm coming from and we're on the same page. So with that said, let's do a little bit of book learning first so you understand what we're trying to do here, and then we'll actually weld up a bunch of these and then cut them apart, etch them, and see what's going on inside. All right, so we got some pretty important stuff to cover here that I think will help you understand what's going on better. So the first thing is tube versus pipe. Universally, people without a lot of knowledge on this stuff will often call, say, this pipe or that tube. Well, there actually is a difference between the two. This here is actual tube, and I know that because of the dimensions of it. Tube, when it's sold to you, is sold by the external dimension. So like this is 1.5 inches, it's 1.5 inches external dimension or diameter. Pipe is sold by the ID, internal diameter, which means that the outside is any number of sizes, and it's all based on the wall thickness, okay? So if you try and buy pipe when you need tube, these inserts may not fit what you're working with, because again, they're going by internal dimension with pipe and external by tube. So that's pretty important. Another very important thing is strength, and that has to do with the DOM tube versus the HREW. And there's a couple other types of pipe out there that, well, you shouldn't really be using pipe for this anyways, by the way, since I didn't mention that. But DOM tube, which is what this is, the tube is drawn through a mandrel and there's no internal weld seam that's raised up at all. That's pretty important because this material is actually stronger by a fair amount than resistance welded. This stands for hot rolled electric welded or electric resistance welded, something like that. So DOM tube is 70,000 psi tensile strength versus HREW is 40,000. There's a significant bump in tensile strength when you go to DOM. The downside to DOM is it costs a lot more. Some places don't stock it, so you have to order it. And it can be difficult to get it in certain sizes, okay? Like if you have some idea of getting a very particular size, it generally is going to be a little bit harder to get. Versus HREW and what they call in the industry poop pipe, so your Schedule 40, Schedule 80, and whatever pipe, all of that stuff, there's a lot more dimensions that you can get with it. So basically this stuff is like 1 inch, inch and a quarter, inch and a half, inch and 3/4, 2 inch, nothing in between that on the OD, okay? Now, does that strength matter? To me, it does. I universally only weld steering systems or 4 links for off-road vehicles, etc. out of DOM tube, just like I only use DOM tube for roll cages. The NHRA, speaking of roll cages, NHRA rules says that you have to use DOM tube. So yes, this is a superior product. It costs more, I get it. That's not good, but you should probably be using it. Now, another important part of all of this is the wall thickness. Now, I'm not an engineer, nor probably are you, but I'll say this. If you're building an off-road buggy or a truck, universally for lower links, for a 4-link and for steering systems, quarter wall is kind of the universal standard. Quarter wall on a street-driven car is probably a bit ridiculous, and you'd probably be using something more like this, which is 3/16 or possibly 1/8. I personally have never used 1/8 inch because I don't build street vehicles. They may use 1/8 inch. So I would do your due diligence and research what the best wall thickness for your application is. And if in doubt, go a little bit bigger than you think. So if you think 1/8 inch will be fine, go to 3/16. Now in the off-road world, quarter is popular for lower links and for steering because of how much abuse the stuff gets from being pounded on rocks. If you ran 1/8 inch, it would be bent like a pretzel on a rock. It's not so much the torque and the power of the vehicles that's the issue. It's the trail damage and the trail rash that will kill links and steering systems. So 1/4 inch, you know, this is 3/16. 1/4 inch is some beefy stuff, but I've bent those many times. So it's to the point that I actually went to aluminum links because I was bending them so much on rocks. And aluminum has a lot more spring back. But anyways, that's a whole nother video. So I think you understand a little bit more about this. Let's talk about what welder you need. Depending on the tube diameter, so like this is 3/16. If you look at these two inserts here, and let me zoom in. I don't know if you can notice this, but there is an absolute massive difference in the size of these two. Now, this is set up for a bigger diameter threaded rod end than this, obviously, but look at the wall thickness of this. If you have a MIG welder, you would safely be able to weld this with, say, a 180 amp MIG welder. When you start getting into guys like this, where you're welding quarter wall tube in this big insert, to be honest, a 200 amp MIG welder is going to be the bare minimum, and you might actually have some significant lack of fusion at that. This is something that I TIG weld. By the way, I only TIG weld rod ends. MIG is capable of doing this, but again, you need a pretty powerful machine because you actually want fusion. You do not want the weld to be sitting on it like caulk. And we'll do cut and etches with reduced settings and look at stuff, and you'll find out in a hurry about why what I'm telling you is the truth. Now, I'm sure a couple of you guys will ask if you can stick weld these, and the answer is yes, you can. It's not the easiest thing in the world to do for numerous reasons, but I will do stick welding in this as well, so we can look at the results of that. All right, guys, so I'm almost done with the book learning, but we're going to need to cover a few more quick things. This here is a diagram of your pipe and your threaded insert. One of the things I learned over the years of welding these is that the fitment of this before you weld is absolutely critical. And what I mean by that is a lot of guys will take the insert, jam it in super tight to that pipe where there's no clearance between the edge of this and the insert, weld it, and then what ends up happening is your Heim joint won't thread into the fitting. Now, that's not a big deal if you got a set of taps, but when you start talking something this big like a 7/8 tap, those are pretty expensive, not to mention that's a left-hand thread on that particular one. So a 7/8 left-hand thread is not something you can just go out to the hardware store and get. So if you butcher one of these up and now you need a tap, guess what? You're screwed. Now there's ways around it. I'll show you later in the video as far as making your own tap. But what I'm getting at is that fitment of this is critical. So the first thing is you need to make sure the inside of the tube is clean. You need to make sure that there isn't a big nasty burr on the inside of your tube. And the other thing is, and this is what I do, you can do whatever you want, I push the fitting tight and then I back it off a little bit. And as far as a little bit, got stuck there a little bit. I don't know, maybe a 32nd of an inch up to close to 1/16. What ends up happening is if you jam that in there and weld it, the weld shrinks, pulls these two together, and because you have a tapered fit here, it ends up compressing in this section right here, which then makes it impossible to thread in. By leaving a slight gap in here from this chamfer from touching that, as it shrinks, it's not going to compress that in, and you should be able to thread your Heim joint directly in it without issue. That's something I learned. Now, another thing that's important here is how much weld do you actually need on one of these? And what I mean by that is this. A lot of guys, when it comes to welding, you want full penetration, full weld, to where this whole thing would be weld, you know, just like that all the way down. The problem is when you look at these thinner ones, that's like less than 1/8 of wall thickness in this section right here. If you try and do a hot full penetration TIG weld or stick weld or whatever in there, what's going to end up happening is you're just going to melt those threads in there to where now you're really screwed and the tap might not even fix them. Okay, so this is actually one of the few cases that you don't necessarily want full penetration welds on something. Generally speaking, what you should be aiming for is a weld that more or less bridges from here and does not melt into here, which I'll be honest, you're not going to achieve this very easily unless you're running a real wide gap in there where this joint insert is sticking way out. You're simply not going to achieve full fusion because you have to melt down this whole edge and this, and it's just not going to happen. What I've found is when you cram it tight and run it super hot with TIG, it's more common to have this than MIG because MIG doesn't have very much penetration, so it almost always will bridge over just like this, the way you want it. Now you got to remember, this whole thing is welded all the way around the tube. The probability of it breaking, even with a lack of fusion in this area, is almost none, especially if you were running settings that were appropriate for this material. So that's all things to consider. Another thing that's pretty important about this, and again, this is my advice, you can choose to do what you want. I do not recommend tack welding and then welding over the tacks on this, and let me explain. The fitment of these inserts in this DOM tube, because this tube is held to such a tight tolerance, has absolutely no wiggle on it, okay? This is a very tight fit. Putting tack welds on this, regardless of where they are, and then welding over it is going to produce a lack of fusion at the tack welds. So my recommendation is set it where you want it, start welding, and try and weld this in 2 steps, so meaning one whole side, rotate it the other whole side, or do it in 3 steps. So 3 times you start and stop. Do not weld these by tack welding with MIG or stick, so just a bunch of tacks. Don't run cold settings on these, that's a huge mistake. Run appropriate settings and try and do it in thirds. And do not put tack welds and weld over the tacks. Like I've showed in numerous videos, when you do that, you get a lack of fusion going over the tack. So before the tack and after the tack, you have a lack of fusion. Now, if you wanted to TIG weld it and you TIG weld tacked it, you'd probably be all right because of how thin that is and because of the TIG process. But with MIG, the last thing you want to do is a giant tack on that. Now, if you did do that by some, not stupidity, I'm not going to call you stupid, but if you did tack it, grind that tack down to where it's paper thin and then weld it. You'd be all right then. Just don't do what I said, okay? Don't put tack welds on it. Now with that said, there's only one more thing I need to cover. Well, that idiot's welding in the background. Let's talk a little bit about specification as far as what materials you can use and what welding processes. In the case of NHRA drag racing, you're allowed to use MIG and TIG to weld, say, roll cages. Your sanctioning body for racing, if you do race, may not allow anything but MIG and TIG. So the fact that I'm stick welding this, say this was a roll cage, you might not be allowed to do that. I know NHRA doesn't allow stick welding, but you got to be careful about it. Now, for you guys that do stuff like I do, where you build stuff and then go out in the woods and destroy it, that obviously you can do anything you want. And it's not that stick is incapable of welding, say, a cage or a tube like this properly. It definitely is, and definitely will make a strong weld. The issue is that at some point you have to draw the line. If you allow stick welding in, then you're going to get a lot of bubbas, no offense to anyone, that are going to basically weld a cage together with 60-10 and likely have a failure due to, well, one, the weld being so much weaker than the base material, and two, weld defects being far more prevalent with stick than probably MIG because of how difficult it is to weld something that's small bore, like 1.5 inch, 1.75 inch tube. So simply drawing the line and saying no stick for a sanctioning body just makes it a lot easier because you can eliminate a lot of the headaches as far as like judging or meeting tech spec for it. And let's be honest, a good weld with even a 60-13 is probably a lot better and a lot stronger than a really crap weld with, say, TIG or even MIG. So it's something to consider what your skill level is at and what you feel the most confident. And always, like I say in every video, make sure you test your own work occasionally. Like, you don't know where things are at unless you actually cut them open and see. You might think that you're 100% hero and have all this root fusion and everything's great, and then you do a cut and etch and see some stuff like we're going to see later in this video and realize that you're doing stuff wrong. Well, let's move on. Well, I got them all welded up, and we'll take an up-close look at them in a minute. I'm happy to report all of them thread in no problem, which is good, and I expected that because I left that little whisper of a gap, and that makes all the difference in the world. If I had to pick one as being the tightest, no doubt the MIG weld and the stick weld are a little bit tighter, but they thread in just fine. No real issue. The TIG is probably the loosest per se. It feels like there's nothing in the threads at all, but it really doesn't make any difference because guess what? All of these worked and we don't have to chase threads. Now, speaking of chasing threads, if you have an issue where you can't thread one of these in and you don't have a tap, one of the things you can do, and I'm not saying it's the smartest thing, but hey, I get it. Like, you can be in a pickle where you need to use it, and guess what? You can't because you can't get anything threaded in. You can take one of the Heim joints, one of the rod ends, and notch the threaded part of the shaft right at the tip in order to create a makeshift tap of sorts. It may help you. If the threads are distorted too much, I don't think that that's going to fix it. Now, I'm telling you this having never done this. I've talked with guys that have that say it works. I have a set of left-hand, right-hand taps up to 1 inch of multiple thread pitches, so I don't really have to worry about that. And ever since I switched to leaving a little bit of a gap there, I don't have to chase any of the threads on these, so that's good. Now, another thing I want to cover really quick is I forgot how these particular rod end, the inserts, the threaded inserts, are coated with oil inside the threads. A lot of them that I buy, for some reason, they must clean them or something. But man, that was a smoky SOB welding on these. So my recommendation is to rinse these out with soapy water at first and then weld them. And if you want to coat it with oil or something inside so it doesn't rust, do it then. But, you know, I get it for shipping purposes and stuff. You need oil in that because if it's rusty, that's a problem. But, man, I wouldn't recommend welding through it on with all that oil on there. Well, let's start out by looking at an up close of the stick weld. So the first weld I did was 332 rods, 7018 at about 100 amps. which I would say is ideal for this 3/16 tubing and this particular rod end insert. It seemed to wet out really good. My travel speed, everything looked really good. And for never having stick welded one of these ever, I would say the results are very acceptable. We'll have to see what the cut and etch looks like, but I like what I see here. Now, my travel speed near the end started picking up. Where I snapped out of it, there's a little bit of underfill, but hey, that's stick welding. You're going to have that. But if you can do anything even close to this, and I'll show you the bottom profile, I would say that you're going to have a strong weld, and it's highly unlikely that this would ever fail. More than likely, it would split and tear this out before this would fail. So that's good. Now, the 1/8 inch 7018 was a little bit different of a story. So the cold start, I didn't have hot start enabled, and guess what? It drastically affected that. Once I turned on hot start, I did a third weld. It was a lot better. But once it got going, it was okay. Little bit hot here. Now, one of the things I kind of screwed up on, again, I don't stick weld stuff like this very often. Well, I've never done anything like this with stick, but small, thin tube. I ran about 130 amps on this, which is normally what I weld 3/16 plate with an 1/8 inch rod. Well, that was a little bit hot because of the gap and the amount of metal I had to fill in there. So I would definitely say 115 to 120 would be far better on this. It would give you more control. So other than cold start, acceptable profile, we'll have to look at how the internals of it compares to the 3/32. That'll be interesting. Now over here, I have an 1/8 inch rod that I backed the amperage down on and enabled the hot start. You can see how much better the start is, and the overall profile looks pretty good. If you can see here, it's a little bit concave. My travel speed likely was a little bit too fast, but for the most part, this isn't too bad. I don't think this would be breaking anytime soon. Not ideal. The weld on the other side here, we'll talk about in a minute. Let's look at the next weld I did. The next weld I did was a TIG weld. I did a single pass running pretty hot, somewhere around 160 amps with 1/16 filler. Generally not what I would do, and the reason is simple. This is essentially all underfilled. I would never weld this with TIG with a single pass. I would go back and do a second pass over this because the throat depth of this weld is going to be on the thin side, and we should see that in the cut and etch. This welded okay with TIG. One of the issues you have with that big wide gap that was there is running enough heat to both join both sides and then melt anything down in the root. You're far better off running a tighter, very tight arc first pass and then going back over it to fill it. By running higher amperage, I think it was at 165 on this, and then just trying to do it in one pass, you're going to end up, like I said, with inadequate throat thickness. So the weld thickness is going to be minimal, and the overall strength of this probably is not going to be that good. So don't do that. Now, the two pass I did here, which this is more of a replication of how I weld these, is a single pass with a tight arc on the first pass, and then I go over and weave it with a slight weave for a cap, and it's done in two passes. Now, when you look at that, not the greatest work, not the worst, but everything's nice and smooth. You can see that it's not concave. We don't want concave. So that overall looks good for a short weld, two passes. This should fare fairly well in a cut and etch when we look at it. Now let's look at the MIG welds. So the first MIG weld, which was done at the recommended settings, somewhere in a ballpark of 320 and 19, I'll put up the actual settings right now. That weld went in okay. It's a little difficult welding around the camera, but this half, so right here, very acceptable, very nice profile. It's not concave, it's not super humped up. I like that. The beginning of the weld, or what looks to be the beginning, that is a little bit humped up. Adjusting my run-in speed as well as some other parameters would likely help that. But overall, this is a decent looking weld. I could have slowed down a little bit, which I did here, and it would have improved a little bit of the, not cold toes, but it's not quite wetted out there. So little small improvements would make this a lot better. I thought, well, if 320 is good, why not crank it up? So I was at 350 plus and 20 volts or more, and then ran it. Well, what ended up happening here is I ended up moving faster, and we have underfill. It's not undercut. It simply is that the weld didn't deposit enough material, and it's sunk in a little bit. So a little bit slower travel speed would have helped. But again, we're going to look at a cut and etch to see if that really improved anything internally for the fusion. I doubt that it did. Now let's look at the last weld I did. Now this is going to be somewhat controversial. I use settings that I used in another video to stack dimes. These dimes don't look that good, but it's the exact same settings, and with a little bit more practice, I could have stacked basically a perfect stack of dimes on these, which for a single pass is something you don't want to do, because when you run reduced settings on thick steel like this, you're going to end up with a severe lack of fusion. And in a cut and etch, we should see how, yeah, it might have a somewhat of a dime stack look, but guess what? It's also going to have no fusion. There's simply no way with the short circuit process to get a dime stack look while having fusion. And Pulse does give a stack of dimes look, but not like this stack of dimes, a cold stack. So I think you know the overview of what we're looking at here. Let's cut this all up and see what's inside. Up first, we have the 332nd 7018 at 100 amps, and the overall weld profile looks like every other 7018 cut and etch. Generally speaking, really good sidewall fusion, not the greatest depth of penetration, and this is no exception. We have a little bit of a lack of fusion there at where the angled part of the thread insert meets the quarter wall tube, and that's going to be very typical of all welding processes, so don't be surprised when you see that in other pictures in this video. But this is about what you're going to expect. And could it have more fusion? Yes. We would have had to have ran a bigger gap, and the problem with the bigger gap is the more heat input and the deeper the penetration gets closer to those threads, now you're going to have to chase the threads. And honestly, the strength that this needs, based on the fact it's welded fully all the way around the tube, I don't know how much more you're really going to gain. If it's of a concern where you want maximal penetration all the way through, then you're going to have to run a bigger gap. Let's look at the 1/8 inch rod now. So this was run at 130 amps, and you can see the bead profile is very similar to the 332 rod. It's a little bit wider. This is the ideal profile that you would want to see with an 1/8 inch rod. And once again, you can see that very minuscule lack of fusion there down right at the root, which again isn't too much of a concern, and if it is, you would have to run more of a gap so the weld metal would more or less hit that better. The 1/8 inch rod was a little bit harder to control than a 332nd, simply because, well, you're putting down more metal and you're running at more amperage. But based on the profile of both of them, I much rather use the 1/8 inch rod, which makes sense because this is 1/4 inch plus steel, so you're going to need more amperage arguably. Let's look at 115 amp pass with 1/8 inch rods and see how that looks. This also has pretty good sidewall fusion and overall acceptable bead profile, and the lack of fusion at the bottom is a bit worse than running at 130 amps. Now keep in mind, your machine at 130 might be like 150. So my machine I know to be pretty accurate, or at least the machine I use to weld this. So 130 definitely is going to be 130. So it's something you got to go by what your weld pool looks like and how the finished weld looks like to determine if you need to go hotter or colder. But again, not bad. I would stick with the hotter settings, to be honest with you. Now let's look at TIG. So this is the first TIG weld I did where I ran just basically a root pass and didn't fill in or cap it. And what you see there is basically just underfill. To attempt to do that in a single pass with TIG, you'd need a 332 rod and likely a fair amount of amperage, probably up near 190, 200 amps. And that isn't generally what I do. So again, underfilled. but the penetration went all the way down and completely fused the root. It's difficult to see in this cut and etch, and I actually tried to do it multiple times to really get a discernible weld, and in this case it just was too difficult. So you can see the left edge of it, but needless to say, there's no lack of fusion. There is some penetration, and this is 100% basically as strong as you can get. It just needs another pass on the top. Now, oddly enough, the one I did on 2 passes is a little bit different. Let's look at that one. So this was done in 2 passes, a root pass and then a filling cap. And if you look at that, oddly enough, we have a significant lack of fusion. Now, there's probably a couple reasons for that. The first thing I notice is that the penetration is actually down in to the thread in insert quite a bit, actually. So my first thought on this is that my tungsten angle likely was going straight in and not angled at the tube as much as it should have. Therefore, it basically bridged over. So that's a tungsten issue for the angle. Also, I ran a little bit less amperage, probably around 160 amps, and that would have likely made a difference. And also, I'll be honest, I didn't prep the surface of this tube. I should have ground it down rather than leaving the dry cut saw marks, so that could have also contributed towards this. And it goes to show, even with TIG, you can end up getting bridging and lack of fusion on something like this. So keep the material clean, go slow enough and run enough amperage and be smart about it, or you can get this. From a functional strength standpoint, I believe that this would not break even if you really hammered on this Heim joint, this rod end, quite a bit. But compared to like that 1/8 inch 7018, this is an inferior weld. I don't believe that this defect extended the whole length of the weld. It's probably in a small 1/8 inch section or so, but again, defects are things you don't want. And how would you ever know that you had something like this unless you did a cut and etch and inspected it? And that's the point of what we're doing here. So unlike the previous one, where had I done a filling cap on that, it would be a 100% solid and about the best weld we've seen today. Here's an example of very similar settings and just a couple things go wrong, and that's what you get. All right, let's move on and look at MIG. So up first were the settings that the machine recommended for welding 3/16 material. Keep in mind the tube was 3/16, but that fitting is quite a bit thicker. So guess what? Our settings are on the colder side. There's a lot of things I don't like in this. So the first thing being on the right side, that plate has almost a straight line. There's a clear lack of fusion starting at the root going all the way down on that right side. And this just doesn't look good. Compared to the 2-pass TIG weld, it has about the same lack of fusion. It's just the cavern per se isn't as big, but it's not really that much better. The wetting out on the sides is basically non-existent. Don't like it. You don't generally want to see this. And this is kind of interesting because I expected it to be a bit better than this. But again, the settings are a bit on the cold side simply because we have more metal here than you would normally have just doing, say, a lap weld on 3/16 thick material. So now let's look at a little bit of a bump in settings and see how that looks. So these settings worked out to be about 180 to 190 amps of output. So pretty decent, significant output here. And with that 035 wire again, which is what I used, the performance here is really good. And this is probably the best that we've seen, arguably. It got full fusion all the way in. It broke down the sides pretty decent, and it filled it all in a 1-pass, 1-deal shot. So no need to do 2 passes like with TIG, or deal with running 1/8 inch 7018 and having a much harder time. So this was by far easier, and the results look really good. Keep in mind, you're not going to get results like this if all you have is a 140 amp MIG welder. And I can't stress the importance of amperage when it comes to wire processes. If you're not running at least a 200 amp capable machine, you simply don't have the output required to be doing stuff like this.
And I hate to be critical about it because I get it. Not everyone has a budget for a $400 or $500 machine, but if you want to wire weld these, that's the minimum of what you need. That's just the reality of it. I can't make magic happen per se. Now, this was done with C25 gas. Had you used C100, 100% CO2, you'd probably have this kind of level result with a little bit less amperage, but you're going to need more voltage to run it anyways. And I still don't think that 140 amp machine is really what you should be looking at, even with a 100% CO2. But yeah, again, like I said, very good looking weld. This is definitely not going to fail. And if you can reliably achieve this on what you're welding, you're really not going to have any problems with strength. What really bothers me the most about wire welding in general is that when you visually look at these two welds next to each other, they literally look almost the same at surface value. Like if you put a coat of paint on them, you'd have no idea that you have a weld like this that's perfect and good, and then the other weld, which looks just the same, that has a lot less fusion. And that's the issue to me with wire, is that visually you cannot tell what the internal of the weld looks like. With stick and TIG, it's far easier to know what's inside. Speaking of not knowing what's inside, let's look at the cold stack of dimes. So here we go. The proof is in the pudding. These cold settings, which is what is commonly used to do that stack of dimes look, granted I didn't do the best job on it in this video, but those are the settings. This is the end result. Now you can tell the same amount of weld material was put down as the other welds, okay? It's just that this did not fuse in, and most of the weld is actually above the plates, not really doing much to help you. Now, beyond that, there's a chunk of porosity that we see there for the first time, and that's very common because when you weld with super cold settings, anything that might be in it that would otherwise come out of the liquid molten metal will now be trapped because of how fast it solidifies. Now that crap you see in that complete lack of fusion at the bottom, that's actually just chemical etchant or naval jelly, so don't pay any attention to that. Now in this picture where the red line is, I put that there because you can't really see it in this picture, but I'm 99% sure that the lack of fusion actually goes up that whole side there, or it's a crack, because I ground that down multiple times and almost the whole length of it has like a raised edge that I couldn't get rid of even when I ground down through it quite a bit. So either the bead cracked off of that, it's a lack of fusion, or who knows, maybe could just be anything, but it's highly suspect. Even though it looks like it fused in there, it's just suspect, so not good at all. And when you look at this, the weld itself actually bit into the 3/16 material of the tube far better than the thicker material, and that's very common with MIG. Anytime you weld two thicknesses, one thick, one thinner, the weld is always going to favor and melt into the thinner material better. So you really got to watch stuff like this with cold settings because you're going to get a real bad lack of fusion on one of the two. Now, realistically, would this fail? In most circumstances, probably not, but there's a couple things you got to remember here. One, this lack of fusion is 100% the whole length of the weld. There is not going to be like some 1/4 inch area that's like this. The whole weld is like this. When you look at all the previous welds, yeah, sure, some of them had defects, but they were probably only in a small section of it, not the whole weld. This is going to be the whole weld. You could have probably taken a toothpick and pushed it through there if I would have tried. Wish I would have. That would have made for a funny video. I also kind of polished up the opposite side just to prove how big that cavern was, and this side's even worse. There is no doubt that over half of it didn't even fuse to the thicker thread insert, and you're talking half of 3/16. I mean, you're borderline almost 1/16 worth of fusion, depending on how much of that actually is fused. I mean, it doesn't look like there's a crack, but you get what I'm saying. I mean, that's virtually nothing. And if this particular rod end was on an off-road vehicle and you hit it against a rock, I guarantee you it's going to crack there. And a crack there means separation, and now you don't have steering. So congratulations. And the proof's in the pudding. Don't run cold settings. Well, let's cash this out and move on to the conclusion.
So in conclusion, I learned a lot today, and hopefully you did as well. I've never done a cut and etch on something like this, so it's kind of exciting to see what happens, and some of the results were a little bit less than what I expected, but for the most part pretty predictable. Hopefully this information in this video helps you tackle a project like this in the future and do so safely. And I'm going to beat a dead horse by saying this again. I cannot stress enough the importance of you doing actual testing to know where you're at, because I don't care what welder on the internet says do something a certain way it works. You have to verify. Trust but verify. And this is a job where if you have some skill, you can safely tackle it. If you're worried about if your skill's in the place necessary to do this, then you need to do some practice plates that simulate this. So like lap welds, fillet welds, etc., and dial it in that way rather than just tackling this with a hope and a prayer that it's going to work. Beyond that, one more thing I want to mention that I didn't earlier is that you want to avoid running downhill welds with any of this. And the reason I say that is, especially with MIG, when you weld downhill, you lose penetration. So if this is tipped on its side and you're welding downhill, what'll end up happening is all that root fusion that you may or may not be getting will completely go away. And what can realistically happen is that really poor stack of dimes weld, that could end up being what your weld looks like, even though you weren't stacking dimes as far as the settings are concerned. So that's something to think of. If you can avoid it, avoid it. And it really pays to set up little wheels or even have a buddy spin it slowly while you're welding to where you have minimal stops. If you can do this in 2 passes, or AKA a start and stop is half of it and then a start and a stop is the other half, it's highly recommended. The fewer starts and stops you have, the stronger the end result will be. And like I said earlier, avoid putting a bunch of tack welds on this. The fit should be good enough to where you don't need that, and that's just going to create lack of fusion. Now, the results out of all of these, I seriously doubt any of these would break, other than I would be highly suspect of that stack of dimes one. If you hit that on a rock, it's probably going to break because the weld thickness just isn't there. And the whole weld is going to look like that, not just a part of it. So with that said, hopefully you enjoyed the video, hopefully you learned something, and thanks for sticking around for it. Until next time.